So I've been getting a bunch of questions about the ACS study guide, so we're going to start off talking about that. Does anybody have a copy of that? Because I keep forgetting. Oh, there's one. I keep forgetting to mention it or bring it to class. That's your ACS study guide. Lots of stuff in it. You should get it if you haven't gotten it already. It may be too late to get it because of delayed times in ordering. I have 2 personal copies, one of which is really crummy, and then the tutoring center has 2 or 3 copies as well. So you're more than welcome to use or borrow those at any time. However, the ACS study guide is for the entire year. You're not being tested on the entire year. You're only being tested on first semester material. Right? So it might be nice to know which questions that you should be focusing on. So if you go to Files on our Canvas site, and then go to Old Exams, and then see this thing that says ACS first semester. That sounds an awful lot like what we're talking about. That's because it is. And if we open it up, these are now all of the questions relevant to first semester material. Anything else, don't do. Okay. Some of which are kind of borderline maybe, okay, like all except 3 sort of. You might be able to explain 3. It's a little bit of a stretch. Okay. It's kind of second semester, kind of not. So you should reference this when attempting the ACS study guide. Of particular note, anything involving carbonyls and aromatic rings you don't do, because that's strictly second semester material. Okay? So please take advantage of that file. It is on Canvas. If you don't want to find it on Canvas, that's fine. Send me an email and I will email it to you. Yes, Mohammed.
I didn't see spectroscopy on this. Oh, okay.
Another chapter. Okay. Yes, there are lots of chapters. Lots of practice. Questions? Okay. So slide that out of the way and let's get started. And what I'm hoping to be a 20 slideshow presentation today.
But is it going to happen?
Probably not. So we'll see what we can do. So we talked about electrophilic additions with 3-membered transition states, or 3-membered intermediates. What we're now going to move into is the 4-membered transitions. Okay? And really it says 4+ because once we get beyond 3, well, they're all pretty much the same. Okay? So for this subclass, our rule is that we need a really small leaving group. Okay? And why do we need a small leaving group? Well, the leaving group is now so small or unstable that it immediately reacts. Okay? So it's a very fast reaction. The reason why that becomes important is that then when we look at our product, the Lewis acid or our electrophile and the nucleophile that attach on the same side of the double bond. Okay? Those of you that have been doing the homework, when we do an addition reaction that our electrophile and nucleophile add on the same side, that is known as what type of addition reaction?
Syn.
It's a syn addition. If they added on opposite sides of the double bond, it's an anti-addition. Okay? You might say, well, why don't we refer to it as cis and trans? Well, cis and trans is ultimately referring to double bonds and kind of rings. If we don't have a double bond or a ring, cis and trans doesn't really apply well. Okay? We can't even really refer to E and Z and all of that. Okay, so instead we have syn and anti. The way I like to refer to it are cis and trans are adjectives. The syn and anti are adverbs. Syn and anti are referring to the action of adding something. The cis and trans are the results thereof. Okay, you're describing the product. So if we take a look at these substrates, okay, if we had our partial positive on our bromine, so there's our electrophile, we have our hydrogen, and then we run into an interesting one with the last one. Believe it or not, it'll be our oxygen. where one of our oxygens is our partial positive. What we need to consider is kind of our leaving group. Is it small? Okay, well, what leaves in the first case? Bromide. Is that small or big? That's really big. Okay, so does this reagent fit in the 4+ member transitions? No. Where did it fit? In the 3-membered transitions. Okay, so no carbocations. How about the next one? What would our leaving group be? I disagree with the statement of hydrogen. It would be hydride. Is that a good leaving group? Is that a large leaving group? No, that is insanely small. Okay, what does that mean? When we're looking at that reagent react, we're looking at it react in that 4+ membered transitions. When we look at the next one in our osmium structure, this one gets a little bit weird. It's not a perfect system, but it works out sort of. Okay. Our electrons leave. Okay. What was our leaving group then? Electrons. Pi electrons. Are those big or small?
Small.
Small, which means we're sitting in our 4+ transition membered system. Okay? So what we're trying to do is think about those reagents and how they can potentially react. You may have a really hard time with that osmium reagent at the end, figuring out how that reacts. Okay? And that's largely because osmium sucks. Okay? So when we think about our reagents, we're trying to come up with patterns and come up with classes behind them. It doesn't work perfectly, but that's what we're trying to at least think about and address. Okay? So depending on that connectivity, we may see cyclic transition states of 4 or 5-membered rings. Okay? In the case shown here, we've got 2 examples. Okay? In the first one, the reagent is HBH2. Where's our electrophile? Hydrogen or boron? Why are you saying boron? We've got a couple different answers for why borons are electrophile. Hybridization. The hybridization of the boron is sp2, meaning it has an empty p orbital. It can accept electrons. That's why boron's an electrophile. If we take it a step further, why could the hydrogen not accept electrons? Okay, well, if we look at the raw electronegativity difference between hydrogen and boron, guess what? Hydrogen's more electronegative than boron.
Really?
Yep. They're very, very close in electronegativity.
How does
Okay.
hydrogen move?
How? How is the physical property? What you may be doing is saying, well, hydrogen is on the opposite side, and that's different than my trend. Your trend is a trend, not a rule. Okay? Hydrogen can be placed in multiple locations on our periodic table. It can be placed above group 1. It can also be placed above group 7, okay, our halogens, depending on whether we're looking at hydrogen as the element, the cation, or the anion. And that is all dictated based off of the electronegativities. Okay? But it turns out that boron is actually lower in electronegativity than hydrogen. Hydrogen is going to take the electrons from boron. That makes hydrogen a hydride and boron even more positive, more electrophilic. So what happens is our pi electrons see the boron and they share electrons outwards. Okay? But then boron wants to have just 6 bonds, just 6 electrons, 3 bonds. So it has to kick something out. What could it kick out? Well, the only thing it's got is hydride. Is hydride a good leaving group? Hydride?
No.
Hydride is now a negative charge on a hydrogen, low electronegativity, very tiny size, bad leaving group. It immediately
Goes back.
reacts with our pi bond, resulting in the hydrogen and the boron being added to the same side of our pi bond, a syn addition. If we look at the mechanism of just our curved arrows, that's what's being shown in our diagram there. Okay? Notice that we're also adding those dashed lines. Those dashed lines are representing the transition. Okay? The electrons from the pi bond react with the boron. The electrons in the boron-hydrogen bond go out to react with the carbon, effectively forming what kind of a transition? A four-membered ring. In this case, we have a four-membered transition state. Right? So looking for those pieces can help us apply what's going on there. We don't actually see an intermediate in this case. We just see the transition states. I don't even know what what you're drawing. What happens in the case of the osmium? Okay, well, the pi electrons come out, react with one of those oxygens. That shuttles electrons to the osmium. The osmium then has too many electrons, so it kicks a pi bond, and another oxygen comes out and reacts with other carbon. The result in that transition of all of those bonds breaking and making is a five-membered ring. The result of making and breaking all of those bonds is a five-membered ring. Okay, now we officially have that as an intermediate. Where are the oxygens relative to the former pi bond? They're on the same side of the pi bond because all of this stuff had to happen at the exact same instant. Right? So we end up with, again, a syn addition. Right? This is organic chemistry. We're concerned about things that are non-metals, so having osmium in our structure is weird, so we'd end up doing some other chemistry. Same deal with the boron. Boron's kind of a weird reagent. We want to get rid of that. In a secondary reaction, we cleave that off. Okay? But the first part we need to pick up is the general regiochemistry and stereochemistry of those resulting reactions. Kind of make sense?
A little bit.
A little bit. Good. So our leaving group in BH3 was our Lewis structure. What's the hybridization for the boron? sp2, which means there's a leftover p orbital, which is currently aimed in and out of the plane at you. Okay, I can place electrons into that p orbital, which is why boron acts as the electrophile. This then goes beyond not beyond the octet, but beyond what boron likes, and so it can immediately shuttle out hydride as a leaving group. That leaving group is a horrible leaving group, so it doesn't officially act as a leaving group because it doesn't leave the structure. It immediately reacts with the structure, and we get that simultaneous result. Okay? Evaluating that reaction comes back to looking at hybridization, considering our stabilities and our leaving groups, okay? The structural representations. All of that is stuff we've already talked about. So it's a question of scaffolding on top of that content. So prettier pictures. So what happens if we mix it with 2Z butene? I actually have this nicely drawn, or do I have to do it by hand? I have it nicely drawn. What would the result be if I react that structure, BH3, with 2Z butene? Perfectly fair question to find on an ACS exam. What's step one? Probably a good idea to draw 2Z butene. So there's my but. Position 2, I have a pi bond. It says Z, so I have to make sure I've done the nomenclature appropriately. Okay. Carbon versus hydrogen, star the carbon. Carbon versus hydrogen, star the carbon. Whoops. Those are on opposite sides. They need to be on the same side because Z means on the same side. So we aren't there yet. We have to redraw that to make sure that we've appropriately shown that structure. Now that we have our starting material, now we can react it. The pi bond reacts by sharing with the boron. Boron now being, whoa, too many electrons, needs to shuttle electrons out. So it can shuttle electrons to that hydrogen, but hydrogen is such a bad leaving group that it makes no sense to show an arrow like that, because that's now saying hydrogen is left. We can't do that. So where could the hydrogen go? Okay. Why does it go to the carbon? Why is that carbon positive?
Because you just lost the double bond.
We're evaluating the pi electrons coming out, forming a bond between our left, or that's my right, most carbon and the boron. That carbon is now effectively with the electrons. The other carbon is our partial positive. It's now a question of matching up the charges and getting our answer.
So would you draw the line from the bond or the line from the H technically?
Where are the electrons?
In the bonds.
In the bond. So where does your arrow need to start? From the bond. Okay? If we look at how our p orbitals align, the electrons end up pooling in one of those p orbitals, react outwards. The electrons come down to fill that empty orbital. Okay? What would our result be? Put a hydrogen on there, right? Put a BH2 over there. So far, so good? Show the other carbon there and be like, oh, we're done, right? Why not? What's the problem? Say that again? We have a chiral atom. That atom's chiral. We have to be a little bit more careful about our approach. Okay? We had two possible reactions. We're going to get enantiomers out of here. Okay? What if we made this slightly more difficult and I added D? What is that D? Deuterium. Why does that make this question even more difficult? We now have two chiral atoms, which means we have to appropriately specify our stereochemistry on this. Okay? So let's go through on the far right and say when this happened, that methyl was wedged. Well, that makes sense. I drew it wedged down there. We go to the far left. Should we draw on our applied hydrogen? We go to our leftmost carbon. What should the methyl be? Okay, I heard dashed.
Oh, it should be the same.
Should be the same as what?
The other one.
Why?
Because they're on the same side.
How did the reaction occur?
They're on the same side, so they have to be.
At the exact same time. It's a syn addition. The hydrogen and the boron were added on the same side of the pi bond, which means the only time I can do rotation is after I've lost the pi bond. Which means when I look at my transition state for the reaction occurring, the orientation of those methyl groups must stay constant. Which means in the product, my methyl group must be wedged. In both of those, or in both positions. What does that make the deuterium? Dashed going away. How could we make this more difficult? Well, actually, let's pause for a second before we ask that question. Are you at least okay with seeing that result? Okay. How does it get made more difficult? So we do get the enantiomer product coming out of this. So we could show either of those as possible products. Okay? That's not going to make it necessarily more difficult because all that will end up happening is we will change both of those positions. Or I could show the hydrogen and the boron being attached on the bottom of this structure, causing it to inverse upwards. How can I make a multiple choice answer more difficult? When hydrogen and boron add across that pi bond, how do they add? Syn. It is a syn addition every single time. Okay. The answer shown does not mean I waited for the exact instant for the syn addition to occur. The answer shown could just as easily have been we did the syn addition and then we let it do whatever the hell it wanted to do to write itself into a more stable conformation. Which would mean our hydrogen and boron could be shown on opposite sides of the structure. How did that happen? I did a bond rotation because of the sigma bond. Which then means when I go through to look at the answers, one of your answer choices will undoubtedly be this. And what is the problem with that structure? It is wrong because what is shown in black is not the same thing as what is shown in red. Okay? Because of that sigma bond rotation. If I rotate that boron down, what happens to that wedged methyl group? It goes away. So you have to be careful. It's not just, oh, they started wedged, so they must be wedged. It's evaluating the chemistry that's happened within it. That makes it much more challenging to deal with the addition reactions. Watch out for post-reaction sigma bond rotations in your answer choices. Okay? Do we need a second reaction? So those of you that have gone through and looked at the textbook, the boron reagent and actually the mercury reagent, both of them involve a second reaction. Okay? When we look at the boron reagent, it's always listed as step 1 and step 2. The first step is the BH3, where we add the hydrogen and the boron in a syn addition across the double bond. Boron we don't want on the structure. Okay? So we need to get rid of it. Okay? It's not an easy bond to break. So we end up breaking it by throwing in peroxide, H2O2, and OH minus. The result is the boron gets substituted for an OH. Okay? In the case of mercury, in that first step we're adding mercury and water across the pi bond. We don't want mercury attached. To cleave the mercury off, we have to add sodium borohydride. What is the reactive part in sodium borohydride? Okay, well, we have sodium as a metal, which means it's an ion, so we have BH4 minus. Sodium you should immediately ignore. If we draw out BH4, what do we see? We get a negative charge on that boron. What is reactive about sodium borohydride? Why are you saying the hydride and not the boron?
The hydrides are just going to dip out.
What does boron want for its octet? 6 electrons. What does that mean? It currently has too many electrons, so what's going to happen? One of those atoms attached to it leaves with the electrons. The reactive part of sodium borohydride is not sodium, not the negatively charged boron, but rather a negatively charged hydrogen. It's a hydride. Okay? Very misleading, but you have to watch out for the balance in electronegativity and the reactivity of those species. Okay? So the mercury ends up getting replaced with the hydride. These secondary reactions are used to cleave off kind of your odd atoms. Okay? So boron, mercury, osmium is one that'll get tossed in there. Okay? So we need to do something else typically to cleave it. Most of those cases, the details and the mechanism is completely and utterly irrelevant. You just need to know what it does. Okay? And yes, based off how we've structured the entire class, you might be like, but Mike, everything you've taught me is about understanding how it works. I know, I apologize, I failed. Okay? You need to know what the result is of these. So that when you see the reagent BH3 THF, it will be partnered with peroxide, and you need to know that the result is a syn addition. The H and the boron add in a syn type fashion. Okay. What ends up happening as our addition? Well, the hydride has to be added. We don't have a choice. But I don't want boron. What's the boron replaced with? The OH in our second step. So BH3 and THF, followed by peroxide and hydroxide, is a syn addition of hydrogen and OH. Okay. Which means when you look at the products, we won't see boron. We'll only see the OH in the place of where the boron would have been located. Okay? In the case of the mercury, Acetate and water or sodium borohydride. This one's a little bit nicer because this is just an addition of H and OH. But you might ask, well, what type of addition, right? Is it a syn or an anti? That would be a valid question. Okay? One that, as we run through those reactions, it oscillates and makes the results virtually impossible to tell. Why is that then awesome for you? You don't need to know it. All you have to know is that when you see mercury acetate and sodium borohydride, you're adding H and OH across the pi bond. Okay? Kind of makes sense? Okay. So let's take a look at the workup on mercury. Mercury reacts to form the alkyl mercury mercuronium ion. That's the three-membered ring. Okay. Mercury is a great leaving group, so what can happen? It can leave, okay, but it must be forced off by a weak nucleophile. Where is it going to get forced off? Here, red, or purple?
Red.
Why is the red one the correct one?
Because it would leave the most stable carbon cation.
Okay. There's two approaches. We can think about the carbocation, which is definitely how I used to think about it, and I'm kind of wavering and not liking that argument quite as much anymore. Okay. But that's fine. Okay. The reason why we don't want to mention the carbocation, is there one? No. Okay. And everybody keeps, oh, I can do a hydride shift. I love that you guys are focusing on the rearrangements. That's awesome. But they only happen if there's a carbocation. If there's no carbocation, you can't do a rearrangement. Okay? So what ends up happening is our oxygen, we have to evaluate our nucleophile. What kind of nucleophile is that? How do you know it's weak?
It's H2O, it's not OH. It doesn't have, I mean, you have to compare it.
It's neutral.
It's neutral. That's how we know it's weak. If it was strong, it would be negatively charged. So it's neutral. Neutral means a weak nucleophile. Weak nucleophiles are important for which mechanism? SN1 or SN2? SN1, which means our weak nucleophile needs to attack which substrate?
Secondary or tertiary.
Our secondary or our tertiary, our more sterically hindered sites. Right? So it'll attack at that position, causing our ring to bust open. We do have an acid-base step. That's why that second arrow is there. Because we're doing an acid-base to neutralize that oxygen. And then we would have that final product with mercury attached. We don't want mercury attached, so we have to get it to leave. Okay? So let's say that again. We have to get the mercury to leave. If a mercury leaves, what's happening to that carbon? Becomes positive. So what do I need to add?
Negative.
A negative. Sodium borohydride is roughly the same thing as saying we have H minus. The H minus in a horribly, horribly, horribly done mechanism. This is one of those things where, remember, you don't need to know it. You just need to know what the result is. And the hydrogen replaces the mercury. Okay? The result, if we think all the way back to the very beginning of how this thing started, so I started with an alkene, and what I end up with at the very end I added the OH and the H across the pi bond. Okay, everybody see that? Sorry, that bond is bothering me. Was there another reagent, if starting with that alkene, that would have gotten to that product? Yes, yes, there is. What would that reagent be?
THF1 and then propanol.
there's an interesting idea. BH3 and THF does what? And then our second step of the H2O2 and hydroxide. What did that add? Hydrogen and OH. What are we trying to add? Hydrogen and OH. So we say, yeah, Mike, that's the answer, except you're wrong. It is a syn addition, so it would add layers to this, but then let's just say it's a syn addition. I could then do this and this, and it'd still be wrong. What's that? What's the electrophile in BH3? The boron. Our nucleophile? H minus. Where's the most positive carbon in our alkene? The left one. Match charges, what happens? It's going to place the BH2 here. If we follow that up with our peroxide, the BH2 is replaced with OH. Interesting. Two reagents that we just talked about, and they place hydrogen and they OH in different locations. And this is where people come in and say, oh, well, it's Markovnikov and anti... Back off with your Markovnikov and anti-Markovnikov nonsense. Follow the charges. Follow the charges. If you approach this and recognize the charge on each of those species, you get the correct result. There's no Markovnikov, anti-Markovnikov nonsense. Okay? Markovnikov's rule happened before electrons existed. That's how old it is. Stop using a term that doesn't take into consideration our broader knowledge. Okay? It's like people saying, oh, I've got the Philosopher's Stone. No, you don't. You're an idiot. Stop it. Okay? So, but this, while this kind of inadvertently brought in an interesting issue, both those reagents add H and OH. They add them in different locations. Okay? But the question I asked is not what happens when you add BH3. What I asked was, how do you make this product without using mercury? What am I trying to add? H and an OH. I'm trying to add oxygen as a nucleophile, but I can't add hydroxide because the issue with hydroxide, it's a strong nucleophile. And what is the alkene? A nucleophile. So I can't add hydroxide, so I'm going to have to hide that nucleophile behind a hydrogen. Okay? But then I still need the alkene to react. It is water. I still need the alkene to react. The alkene acts as an electron source. It can't react with the HOH. What can it react with? How about H+? Okay? Or, because H+ does not officially work because it's not a neutral species, how can I get that H+, Joey? With a fully correct answer? H2SO4. What happens? What's the most reactive thing in this solution? H+. Where does the H go? To the more Did you do that intentionally? Goes to the more negative carbon, leaving behind a positive charge. What happens now? The result is that product. Okay? What do you know about mercury? It's bad, toxic. Okay? So why would I ever run a reaction with mercury that I know is toxic and kills things that I could have just used sulfuric acid and water for? What's that? If you can elaborate on the reliable, I might accept that. No, but not a bad concept. We're looking at our first step as a protonation versus our nucleophilic attack or our coordination. So the protonation isn't going to happen in a different spot. What's the issue with the carbocation intermediate? The rearrangements. Right? If I have a structure where I could do a rearrangement and I don't want the rearrangement, sulfuric acid in water is a horrible option because it won't reliably just add H and OH across the pi bond. It'll add the H, and then the OH could be added at any place where that carbocation is more stable. So if I don't want the rearrangement, what do I need to do? Make sure I don't have a carbocation. Which mechanism does not have a carbocation? The Mercury reaction. The Mercury reaction prevents the rearrangements because there is no formation of a carbocation. So it's looking at each of the stages within it and thinking about those synthetic mechanisms along the way. In this case, do I care about rearrangements?
No.
Why not?
Secondary is the best.
Secondary is the best carbocation I can get. Rearrangements aren't going to matter here. Which reagent should I use? Mercury or the water and sulfuric acid are both fine. Neither one is a preference. You would never see both of them listed as a possible answer.
What's the nucleophile with the Mercury reaction?
The nucleophile with the Mercury reaction is water. Okay. You're right when you say Mercury as well, Mohammed, because the Mercury acts as an electrophile first, then as a nucleophile immediately, okay, to form the mercuronium ion. But then our active nucleophile is water when it does its nucleophilic attack. Okay? So again, trying to find patterns and commonalities. Once we have the commonalities, then we can start to say, well, why did we invent this other reagent? Okay? Almost everything we do has a single purpose associated with it. We don't typically do multiple different reagents to do the same thing. Okay? There's some variation within that. Okay? How do we remove boron in the second reaction? Okay. This is our hydroxide, or our peroxide and hydroxide. Okay. It is a rather complicated mechanism. The way that I prefer to look at it, that I think is a little bit more straightforward, is the reactive species or the reactive effect of boron. Why is boron special as a reagent? The sixth thing. It has an empty p orbital, so what can happen? It can shuttle electrons into the boron, but then what? Boron then doesn't like it, so it needs to shuttle electrons out. What can those electrons then immediately react with? We have that weak oxygen-oxygen bond. We saw that already when we looked at the MCPBA, our peroxy. That bond is already dying to split open. The reason why I would evaluate this is, what does that mean happened to that wedged carbon? Is there any time for that carbon to rotate? No. Which means, where does the OH go? The exact stereochemical arrangement that the boron was in. You'd get a retention of stereochemistry there. Is this the correct mechanism? Not by a long shot, okay? But it is close enough for horseshoes or hand grenades. I wasn't trying to be good. Practice. Give me products. Upper left, what do you got?
What?
Upper left, what's your answer?
Hydrogen and OH.
Do we need to show the hydrogen? No. Okay. Questionable to show it. Okay. You might see it on the ACS where they have shown it. sort of. What they would probably also add would be maybe like a deuterium here. And they would do that because you then have stereocenters. And we would have to specify the stereochemistry. So let's go through and imagine what that would look like. How would we fix our answer to make sure that we get the correct one? So wedges and dashes?
No, that needs to be a wedge.
They both need to be the same.
They both need to be the same. Okay. So possible answer choice, you could get this structure, then them both dashed, and then one wedged and one dashed, and then one answer saying two of the above are correct.
Does it matter if that?
Okay. Does that make sense?
The wedges.
Would it matter if the OH is on the top?
Score 2 dashes because of the deuterium being there.
Remember, you can either the alkene can react above or below. So our H and OH, as long as they're both on the same side. No.
You're saying like one's wedged, one's dashed, and then they're both.
Both wedged, both dashed, one wedged, one dashed.
It's like or two that are the same.
Or your
two
last
that are
answer
correct.
saying two of the above are
Let's do
correct.
that one then.
Does it matter if the OH is on the top compared to the second? Because they're both
Compared
primary.
to the location of where that OH is? No.
Does that matter? Okay.
Nope, that won't matter.
Where did the deuterium? Or did you?
I just added it. I literally just added
Do you
it.
have to do deuterium and?
Typically, they would add deuterium because the issue of adding, say, a methyl is the methyl is now sterically different, which then means you get a favoring of where the H and the OH go. So they weren't testing you on the regiochemistry, they were testing you on the stereochemistry of your addition.
So if there wasn't a deuterium, like the original product,
Yes.
does the OH need to be dashed or wedged? in comparison?
Do we need to show wedges and dashes on that OH?
No.
Why not?
No stereo.
It's not a stereo center. Okay. 2. If we go straight across, upper right. We add H and OH. Right? So there's the OH.
Yes. So. OH on the outside.
Goes the other way. Remember, your boron's your positive, your hydrogen's the negative. If we go back and look at our resonance structures for the alkene, positive on the inside, negative on the outside. The hydrogen is going to the inner side. Okay. Lower left-hand corner. OH goes there. We got a little bit more than that. So I'm hearing an OH goes here and an H goes here.
No, the hydrogen will go on the tertiary.
For the same reason from the upper right-hand corner. Okay. This is where specifying your charges. More than likely positive, negative, positive, negative. The negative hydrogen goes where? To the positive position. Our answer is actually the other way around. The OH is out here. The hydrogen goes to the tertiary. This one brings up another issue, though. Not only do we have to be concerned about the regiochemistry, where did the hydrogen and the OH go, but we now also have to worry about stereochemistry. Is that valid? One wedge, one dash?
No. The OH needs to be wedged.
Do I need to show the hydrogen?
Yes.
I can imply hydrogens right and left. That's not a problem. I didn't show the dashed hydrogen where the alcohol was located. I don't have to show the wedged hydrogen. Is this the correct answer?
No, it needs to just be a straight line.
No. I don't know where you're going, Nolan, but no.
He's like, I'm right.
So you have to show the other way.
You do not have to show the wedged hydrogen. By showing the dashed, what does the hydrogen have to be? It has to be wedged. I don't have to show it.
You get that wrong in smart works if you do that. You're not supposed to show the hydrogens.
Not necessarily.
No,
you
in
have to
Mark's
show them
law.
all.
Oh yeah, that's right. You show.
Okay. So what I'm trying to show in this answer is that your response was they both need to be the same. They both need to be wedged. So you see wedged and dashed, you may say, oh, that's wrong. But you have to be careful on what's being labeled as wedged and dashed. It's not just I only have wedges or I only have dashes. You have to watch out for the other pieces. Okay? Make sense? Last one. Okay, so I'm hearing, does that one happen twice? And that's because there's 2 pi bonds. We might say, well, it happens twice. Well, let's see what happens when we do it once. What do we get?
Goes on OH on the primary.
The OH goes to the primary, and I end up with this structure. I now still have a pi bond, so I could potentially do it again. Pause a second. What functional group do I have? That's not true. I have an enol. And what do the enols do? Tautomerize or tautomerize to give us the carbonyl. Okay? You have to watch out for it. This one's actually a bit trickier than that. The alkyne won't react cleanly with BH3 under these conditions. We need a special form of BH3. So it's usually, because I don't think I have it on the next slide, I think it's something like HB, and then you'll see SIA2 in THF. Okay. SIA is a special substituent attached to that boron that facilitates or forces the addition of that hydrogen across the double bond, across the pi bond. Nothing to do with silicon. Right? So we can change that boron reagent to something else. It's still going to follow the same general types of patterns of the chemistry. So don't just say, oh, it's not BH3, so I have no idea what to do. Do you have boron? Yes. How many things are attached to that boron? 3, which means it has an empty p orbital. It can still act as an electrophile like I've seen in BH3. What pieces are attached to it? Well, hydrogen and then SIA. What the hell is SIA? I don't know. So guess what? Make the hydrogen do it. Make the hydrogen come off as your chemistry, and then everything follows according to what you've already seen. Okay?
So they might just add that SIA.
And I don't remember exactly what it is, but it's some extra piece like that. Remember that whole I don't memorize things very well? When it comes to reagents, I'm really, really, really bad.
For this mechanism, is it safe to say like the OH always goes to the least substituted?
So, and this is where people will try and call out patterns, and I'm fine with you trying to go through and look at patterns. Where does the OH add when we're using the boron reagent?
Positive, negative.
We could go through and say positives and negatives, right? But positives and negatives weren't shown. What was shown? The substitution patterns. Okay? Where does the OH go in all of these cases when we look at the substitution pattern on our pi bond? It goes to the least substituted. So is it okay to make that statement? Well, is it valid?
Yes.
Yeah. Okay? Are you ignoring the chemistry behind it? Yes. But it's valid. So is it okay to do it? Yeah.
Okay.
I may not be happy with it, but you'll be right, so it's okay. Okay?
All that matters, right?
So our boron reagent looks similar to other reactions. Right? It looks similar to the mercury reaction because we're adding H and OH. It looks similar to acid and water because we're adding H and OH. The big thing that stands out for the boron reagent is that it adds it in the opposite direction of what you would expect. Okay? Based off of Markovnikov's rule. I know. Okay? But what I'm trying to do is address where those differences are coming out. Make sense? Do you want the full mechanism?
No.
See, look at that. You skipped
Which kind of slides us into chapter 19, and it's looking at reduction and oxidation. Right? What you should have remembered from Gen Chem, gain of electrons. Really?
That screen's a lot brighter than
Yeah, this one sucks. This one's like blurry and dull. Damn.
Did nobody else notice that? Gain of electrons begins with GER, and loss of electrons is LEO.
Yeah, Leo goes first.
Leo goes GER. Okay, so I apologize for that typo on that slide. I have no idea how I goofed that. Okay. So that's what you should have remembered from Gen Chem on tying oxidation and reduction. Look at the reaction shown. Oxidation or reduction? Leo is another name for a lion. Lions are cats, and cats, grr. Leo the lion
Technically, cats don't grr.
says grr. So, back to the reaction. Oxidation or reduction? Okay, so there's an easy cop-out, which is fair. It's both. It has to be both if we're saying redox. Okay, what happened to the organic compound? Was it oxidized or was it reduced?
Reduced. Grr.
Oxidized. It lost a
Oh, we just look at the electrons. What atom lost electrons? So carbon is missing an octet in one of those?
4 carbons.
No. So the whole role of gain of electrons and loss of electrons becomes a pretty useless moniker when we move into organic chemistry. We can apply it if we go back and calculate oxidation states. You remember back in Unit 1, I said we need to know how to do formal charge, oxidation state less slow. Okay? And I said, does anybody want me to show you how to calculate it? And you're all like, no, we don't need to worry about it. This is where you would need to worry about it if you wanted to go through and calculate it. Conveniently, there's other rules. Why do we call it oxidation? The most common form of an oxidation reaction is the addition of oxygen. We've increased oxygen bonds. What would be reduction then? Decrease oxygen bonds. So cool, we have a new definition.
There ain't no oxygens.
Thank you. So we've got a bit of a problem there. Okay? So let's take a look at, say, a classic oxidation reaction. CH4 plus O2 goes to CO2 plus H2O. This is an oxidation reaction on the carbon. You could go back and use your Gen Chem knowledge and look at your oxidation states, calculate them, and do all that fun, fancy jazz. And you'd say the carbon was oxidized. What happened to the carbon? Well, we used our definition. Carbon did what? Gained oxygens. In the process of doing what? Losing hydrogens. I can reference the oxygen. I could also reference hydrogen. In an oxidation reaction, I'm losing hydrogens at the expense of gaining oxygens. Okay? I don't have to gain oxygens, but one of these two cases has to be true. What happened to our carbons? They gained hydrogens. And we would know that because we remember that we have implied bonds here, and that when we shift across, we've added hydrogens. So I've added hydrogens to the carbon, which then means I reduced. Okay? For those of you that don't understand, what happened when we did the oxidation from CH4 to CO2? We gained oxygen and we lost hydrogen. In the case of going from our cyclopentadiene to our cyclopentane, what did we do? We gained hydrogen. Could that be an oxidation reaction? No, because the oxidation is loss of hydrogen. So what happened? I did the opposite of it. The opposite of oxidation is reduction. So by looking at a reaction, I can try and classify it according to oxidation and reduction and using some other terms to help me kind of whittle my way through without having to do calculations. Okay? We could look at our oxygens. This is our tweak to our rules. Okay? I would make an argument that oxygen is way too specific, and what we actually need to adjust in here is not decreasing and increasing bonds to oxygen, but decreasing bonds to electronegative atoms. What is oxygen? electronegativity, okay. And if we look at our oxidation, that's an increase in electronegative atoms. Can we apply this new definition to the one shown above? What new atom has a different electronegativity? What are you saying, Joey?
SP2 versus SP3 carbon.
Carbon to carbon, there's no difference in electronegativity, except the carbon in my starting material is sp2. The carbon in my product is sp3. And based on what we remember talking about multiple times now throughout the semester, what happens to our electronegativity as we increase hybridization? It decreases. So as we go from sp2 to sp3, we've increased the hybridization, we've decreased the electronegativity, we've done a reduction here. Okay? Our oxidation states, homolytic versus heterolytic, to get our oxidation states. If you want to know that, talk to me after class. I have no problems walking through and discussing that with you. It's just not worth spending our time on. So take a look at these reactions. I will give you 2 minutes. Oxidation. Next one. Neither. Reduction, oxidation, or neither. What happened to the carbon? Yeah, we added an oxygen, but what did I replace? I lost an electronegative element for gaining an electronegative element. That is not an oxidation or reduction reaction. That's a standard substitution. Bottom one, what happened? Reduction. Look at what happened to your carbon.
Those are my guesses, but
Our far right, we have an oxidation because we've removed hydrogens. It's a loss of hydrogen in that top reaction. Next one down is oxidation. And then the last one is oxidation. Right? So, it's tricky. It takes a little bit of practice. I didn't give you a whole lot of time. I only half apologize. 19. So, because I've received a couple questions about the extra credit homework. It is extra credit in that if you do it, it's not, or if you don't do it, it doesn't affect your grade. Okay? Is it on the exam? Yes. You should do it. Okay? If you've decided that your homework score is perfect enough that you don't want to change, or you can't change your smart work score because you already have full credit, you have a total above 90% and you're going to get full credit, that's fine. What you should do with the extra credit is still do it, but don't draw stuff in because it takes time to draw it in. Look at the homework, write it down, click check answer. You didn't enter anything, so it says you're wrong. But the instant it says you're wrong, what can you now do?
see the answer.
See the answer, and you can compare the answer to what you drew. Okay? That way you can move through the homework much, much quicker, and you don't need the points. If you need the points, all that's going to happen is I take all the total of all your points across all the homework, and I divide by your total possible homeworks. Well, the last two won't count in the total possible. Okay? Your SmartWorks homework is only out of 60. You can't get higher than 60. Okay? So when we go through and look at our alkene oxidation reactions, right, we're starting with an alkene, and we are increasing bonds to oxygen. We've already seen a reagent that increased bonds to oxygen. Which reagent was that? Actually, two of them. MCPBA, that was that peroxy thing.
Is that going to be on
On the final? Yes. That's why we're talking about it. They will write out MCPBA on the very first page. So you got the directions on the very front, the cover page. You turn that page over. On the back of that, you have a periodic table. And then you have a bunch of acronyms like MCPBA and the structure shown underneath it. So if you see a weird acronym, you're like, I don't know what that acronym is, flip to the front page and take a look at it. If you still don't know what it is, guess and move on. If you have time at the end, you can raise your hand and be like, hey, Mike, can you take a look at this? I'll be like, I'll tell you that. Officially, I can't, but I mean, I won't tell you. I won't tell you because, you know, recordings and all that. The other reagent we saw, OSO4, osmium tetroxide. That was forming that 5-membered cyclic structure. Okay, the oxygen being added on the same side. If you take a look at the result, you notice we don't see osmium in our product. That's because what did we follow the osmium up with? A step 2, and that step 2 is what has gone through and replaced the osmium. So cleaved it out of there, we get the oxygens on the same side. So 2 of those reagents we've already looked at. Okay, the rest of them are new reactions. Okay, so what we're looking at is our penta intermediates in these cases. Okay, we're forming some kind of 5-membered intermediate ring structure. So the pi bond is reacting outwards. Something is immediately reacting back with the pi bond, which means in all of these cases we're getting a syn type addition. Okay? But if we look at all of these cases, and notice that we have 5 possible products coming out of this. 1, 2, 3, 4, 5 across the top. Only 2 of those do I care about syn addition. Which 2? The ones on the right. Top right, bottom right. Why do I not care about the others? There's no stereocenter. Okay? The result in those products is a carbonyl formation. Okay? Officially 2 carbonyl formations. So since there's no stereocenter, I don't have to worry about syn or anti-additions on those. Okay? So what we're looking at is that kind of tiny leaving group. And yes, it's kind of weird in quotes because we have the metal oxides. And what's happening is our pi bond reacts upwards. The leaving group, if we show it in purple, is the pi bond. It's really horrible, but that's kind of what we're saying it is. Leaves, which then exceeds our metal, so the other pi bond comes down and reacts. Okay, so that's forming our 5-membered ring. The other one is ozone. If we look at ozone, we have that positive oxygen in the middle. Why does it not just do that? It exceeds the octet. So just because there's a positive charge, remember that's not necessarily the reactive atom. That center oxygen can't accept electrons. Okay, so could our electrons do that then?
No,
Why not?
because of the negative charge.
The negative charge. Negative and negative doesn't work. So we could go this way. We have this exceed octet, but then we can stabilize that positive charge. We also now have effectively a large buildup of negative charge next to each other. That oxygen comes down and closes out our ring. Okay? So what we're looking at is that syn addition in all of these cases. What then happens in the subsequent steps is how do we break it apart? Okay? There's our pi bond showing that. Yeah, more pi bonds. For those of you that move into second semester, or for some reason want to get really far out there and take a look, I will post a video on the Diels-Alder reaction. It's another alkene addition reaction. It's a little bit weird though. Why is it weird? What are we reacting?
A ring.
We aren't reacting a ring, we're making a ring, but that makes sense because all of the reactions we've looked at with our electrophilic additions have been rings. What are we reacting? I'm reacting alkenes with alkenes. How many alkenes am I reacting? 3. And in the process of reacting those 3, I make a new ring structure, and I have another pi bond. How that reaction occurs is the Diels-Alder reaction. We might look at it and say, well, that doesn't make any sense. There's no charges, anything like that. That's why it gets named after Diels-Alder. Diels and Alder. Okay? So I'll post a video on that. It's the lab we start second semester with. we'll kind of see what happens. Hopefully we won't talk about it again. Our syn dihydroxylation mechanism. So this is where we talked about the osmium forming that 5-membered ring. The pi bond comes out, reacts with one of the oxygens. We break the pi bond. We now have too many electrons. Pi bond comes out, forms our 5-membered, officially called an osmate ester. Why is it an osmate ester? Why is it an ester? Is a carbonyl and an oxygen bound to the same atom, and that extra oxygen is only bound to other carbons. Why do we call it an osmate ester? The middle atom is an osmium. Yay, osmate ester. Okay? That is our intermediate structure. That's what's happening with the osmium. That's officially our syn addition. We have to cleave the osmium off. Notice, how do we cleave it? We cleave it using several steps, which is a fancy way of saying, I don't know. Right? So we cleave it off. The reagents necessary for that, unfortunately, it's all over the map when we're looking at the osmium reaction. And this is kind of where I want to end on this one. You'll sometimes see peroxide listed out as a reagent. If you go back a couple slides, I had NMO and question marks, or HSO3, okay, listed as a reagent. Okay. Ultimately, you see OSO4, you add OH in a syn, 2 OHs across a pi bond in a syn addition, period. Don't worry about any weird intermediates, anything like that. That's the result. Right? So if I start with this as my starting material, I see OSO4, and I don't know, how about let's draw this little thing here. Going up, yeah. So I'm reacting this with it. The result is that's where I was going. Okay, what am I reacting it with? A pineapple. What do I get as a product? I get that. What if instead I react it with a banana? What do I get?
Nothing.
That exact same product.
It's actually a pretty good banana.
What if I react it with?
A person.
Is that an alligator?
Let's go with alligator, and I'm done with time, so I can't draw anymore. But let's say that was an alligator. What do I get? The exact same product. Syn addition, OHs. Okay? That's what our OSO4 does. Okay? And with that, we'll end today.